Before we start some problems in section 11.2, I'd like to make let's do some practice with summation notation. This is the way I thought I could say it in general. Sometimes you want to change the index that you're starting your sum at. And if you do, let's say that we had looked at one that was started at 3 and we wanted to start the sum at 0 instead, well, then we would be subtracting 3 from the starting index, and what you do then is just add 3 to all the k's that you see in the a sub k. So look, the sum from k equals 3 to infinity, you'd have a3 plus a4. And same thing here. If you started with k equals 0, you would have a3 plus a4, etc. So let's see. Let's try to express this in summation notation, and then I'll change the index just to show you how you could do it. Notice this is 2 cubed over 3 cubed, 2 to the 4th over 3 to the 4th. So first you notice that pattern, and then, well, let's write it. 2/3 cubed plus 2/3. First you hunt for the pattern, and we see it's a simple one, and that will be the sum of 2/3 raised to the k power starting at k equals 3 to infinity. If for some reason you want to, you could start it at k equals 1. If that's for some reason you wanted to start at k equals 1 to infinity, that would mean that we had subtracted 2 from the beginning index, so we would add 2 to k wherever we saw it. So that would be 2/3 to the k plus 2. Notice this one starts 2/3 cubed. This one also starts at 2/3 cubed, 1 plus 2. So it's just a little trick for changing the index in some way if you want to. You'll see some problems where you want to do that. Here's an example where you might want to simplify what's inside by making the n plus 2 factorial n factorial. So you might think, well, I'd like to just write this a little bit differently, and I would want to subtract 2 from this. Subtract 2 and make it n factorial, and then subtracting 2 from n plus 2, I would get 1 over n. So I think I'd like that, but if I subtract 2 in there, I have to add 2 to the starting index. So this is exactly the same sum as the sum from n equals 2 to infinity of 3 to the 1 over n factorial. And you might prefer that way of writing it. Notice when n is 0, we have 3 to the 1/2 over 2 factorial. Here, when n is 2, we have 3 to the 1/2 over 2 factorial. So it's exactly the same sum. This is a theorem that is very tempting to use because it's very helpful, but you only can use it under certain circumstances. If the two series, sigma a sub k and sigma b sub k, both infinite series, if they both converge, you can mix these terms up just the way you do in a finite sum. Certainly if you had summation a1 plus a2 plus a3 and b1 plus b2 plus b3, of course you have the commutative property of addition, and you could write that as a1 plus b1 plus a2 plus b2 plus a3 plus b3. But you can also do that with infinite series as long as these converge. So let's see, let me write that out and show you what it means. This means that if you have a1 plus a2 plus a3 plus forever, you have that series, and you're adding to it the series b1 plus b2 plus b3 forever. that you can add them pairwise. A1 plus A2, B1 I mean, A1 plus B1 plus A2 plus B2 plus, and so on. You can do that as long as these two converge. Actually, how it turns out is if any two of the three converge, you know the other one does. And also, if sigma A sub k is a convergent series, in other words, if it makes any sense, you can certainly move a constant from inside the summation to outside. It's your distributive property. We're saying that the sum of CA1 plus CA2 plus CA3 plus forever is equal to C times A1 plus A2 plus A3 forever. But the only time you can do something like this is if you know that the sigma A sub k is a meaningful mathematical object. You can't factor C out of something that makes no sense, so you have to make sure that the series are convergent before you can use these little algebra techniques, the distributive property and the commutative property. An example where you can is here. I'm going to first of all separate the fraction into 4 times 1/3 to the k. I see 4 times 1 over 3 to the k, plus, and then you have 2 to the k over 3 to the k, which is 2/3 to the k. So these are the terms of the series, and I can split them because I know that I can split them and I can factor that 4 out. I know this will be 4 times the sum, 1/3 to the k. I don't have to take the 4 out, but I can. Plus the sum of 2/3 to the k. And k is starting at 0 in both. And that's okay to do because r in both cases has absolute value less than 1 and it's going to converge. The standard example that textbooks use or that authors use to show you how you do have to be careful is, let's look at sigma j equals 1, let's go 0 to infinity, of -1 to the j. And we're also going to look at the series j equals 0 to infinity of -1 raised to the j plus 1. So let's look at each of these. This one, we're starting j at 0, so -1 to the 0 is 1, and then you'll have an odd power of -1, an even power, an odd power, an even power, an odd power, and so on. And we get that series. Now, let's see, does that converge? Well, no, because let's look at the partial sums. I'll do that in a different color. Let's look at the sequence of partial sums here, Sn. Okay, well, the first term, the sum of the first term is 1. Then we add the first 2 terms and we get 0. Then we add the first 3 terms and we get 1. We add the 4 terms and we get 0. Then we add 1. We add -1. And you see that Sn certainly does not converge. It just goes 1, 0, 1, 0, 1, 0. It diverges. It has no limit. Now let's look at the next one. It's very similar, but we're starting j at 0. So the first one is -1 to the 1. So it's -1. And then we have +1, -1, +1, -1, +1, and so on. And we get exactly the same result for its sequence of partial sums. For this one, the sequence of partial sums, well, the first partial sum is just -1. But the second one, we add the first 2 and we get 0. The next one, -1. The next one, 0. S5 is the sum of the first 5. So we have -1 and 0, and we'll keep going. We see that it certainly diverges. So these two series are not convergent series. We can't use them in any type of algebra or adding them together or doing anything at all with them because they have no meaning. However, notice if I write a series this way, the sum from j equals 0 to infinity, and I make my jth term -1 to the j plus -1 to the j plus 1. In other words, if this up here is a sub n and b sub n, here I have sigma a sub n plus b sub n. Well, this is simply from j equals 0 to infinity, every single term is 0. See, if you add these terms, the first terms, the second terms, you just get 0. So this is the series 0 plus 0 plus 0 plus ... and it certainly converges. It is 0. So you cannot write this series as the sum of these two series because they don't converge. And this problem is it's not one that you would think of how to do it right away, so you learn from the example. This is using the theorem that we just had. Given this series that sigma 1 over I squared from I equals 1 to infinity is in fact pi squared over 6. And it is, I don't know how they figured it out, but it is pi squared over 6. This infinite sum is equal to pi squared over 6. So, in other words, this is the limit of the sequence of partial sums. Find the limit of the following series. Well, there's let's write what this series is. Let's write it out. It is, well, one way we could think of it, j equals 1, so it's going to be 1 over 2 squared plus, and then I'll have 1 over 4 squared. Notice I'm not multiplying out or using my calculator. I want to keep things in a form where I can see a pattern. Plus 1 over 6 squared plus ... plus 1 over 2j squared plus, and on forever. And that is equal to, oh, well, we don't know what it's equal to. Sorry about that. Let me go back and erase that. Okay, so we want to know, what is this? Well, I know that it's half of these terms, isn't it? It's this one plus this one, and so on. It's the ones that have even squares. But that doesn't help me. It's certainly not necessarily half of pi squared over 6. So I have to look at it a little bit differently. Let me write this as summation 1 over 4j squared. I mean, it's just something you can try. But I look at that and I say, oh, that's 1/4 times this. So that will help me. I'm going to take the 1/4 out using the theorem. Because we know this is a convergent series. So I can factor the 1/4 out and write 1/4 the sum of 1 over j squared, and it started at j equals 1 to infinity, was right where this one started at. I want to check that because it's the sum of all of those terms that is pi squared over 6. So this is 1/4 times pi squared over 6, or pi squared over 24. When I looked at it this way, I saw something important that's going to help me. I saw that it was half of these terms up here, but it didn't help me get the sum. So I thought, well, I'll try something different. I'll just, oh, this is 2 squared j squared, and when I looked at it this way, I saw, oh, this is a convergent series. I could factor the 1/4 out, and I'm left with exactly what I know was equal to pi squared over 6. Okay, the next part of this problem, still using the given. Well, let's write out some of the terms. K starts at 0, so the first term is 1 over 1 squared, which is 1. And then I have plus. When k is equal to 1, I have 1 over 3 squared. When k is equal to 2, I have 1 over 5 squared. So now I'm getting the odd squares. 1 over 7 squared plus ... So if you look back at the original series that was given to us, this one, we see that the 1 over 2j squared gave us these, and the 1 over 2k plus 1 squared is giving us the odds. So we realize when we see that the sum of these two add up to pi squared over 6. Because these are, if we put these together, which we can, because we know this one converges, and we know that the whole thing converges. So if 2 out of the 3 are convergent, we know that we can say the following. The sum from k equals 0 to infinity of, and let's go back up here and look what it was, 1 over I squared, 1 over I squared is equal to the sum from k equals 0 to infinity of 1 over 2, I'm using k, so let me write k here instead of I. K equals 0 to infinity of 1 over 2k squared plus the sum of the odds. K equals 0 to infinity of 1 over 2k plus 1, that's odd numbers, squared. And we know that this one is pi squared over 6. And this one here was pi squared over 24. And we can solve now for this series. Summation 1 over 2k plus 1 squared. And if you solve for that, just subtract pi squared over 24, you get pi squared over 8. So this series here is equal to pi squared over 8. Well, there's one more problem here. I wrote the 3 things that we now know. We were given this series here, that the sum was pi squared over 6, and we found that the ones with even denominators added up to pi squared over 24, and then subtracting that from pi squared over 6, we got the sum of the odd squares in the bottom. So we have those 3. Now, before we worry about this, let's just write out some terms. Always just start writing. M starts at 1, so I'm going to start with minus 1 squared, 1. So I'll have 1 over 1. Then I'll start changing sign. Minus 1 over 2 squared, plus 1 over 3 squared, minus 1 over 4 squared, plus 1 over 5 squared, minus, and so on. So I look at that and I think, well, does this tell me anything up here? Yes, it does, because look, the positive, the ones with a plus 1, are the terms of the series that have odd denominators, and that is exactly this one here. And does it start at 0? Yes. So if we add up just the odd ones, this is the sum from I equals 0 to infinity of 1 over 2i plus 1 squared. And now subtract the sum I equals 0 to infinity, I think I have to check that 0, of 1 over 2i squared. Now, is that right? Let's check the beginning indices. When I is equal to 0, I do start with 1, and then I have 1 over 3 squared, and those are the ones I'm adding. Now I want to subtract this one, etc. I want to subtract the sum of all the ones that had even denominators. And if I start at I equals 0, I can't. I have to start at I equals 1, so I correct that. I equals 1. And so I get, now I get 1 over 2 squared. That's right. So right there, when I check that, I should go back and change this. This was an oversight that I didn't see. This should be 1 here. We don't have 0 in the denominator. All right, so, but they're still the same values. All right, so I get, well, this one was pi squared over 12. And this series had a limit of pi squared over 24. So let's see, what do we get? Pi squared over, let's see, 2 pi. I think I better multiply this by 2 and 2, so I get 2 pi squared minus pi squared, so it is pi squared over 24. I'm really sorry. When I copied this down here, it's not a mistake that we made in the problem. I just copied this down incorrectly. I'm sorry. This one was pi squared over 8. So this is pi squared over 8. I knew when I did this on my paper, I knew I didn't get that answer. So this would be 3 pi squared. It's 2 pi squared over 24, which is pi squared over 12. So the answer is pi squared over 12. I'm sorry, I don't know how to edit, and I don't want to do the whole thing over again. Let me go back and show you what I did as a mistake. See, there we got pi squared over 8 correctly. And then I copied it down as I moved it so we could still see it, and I wrote the wrong number here. So there's no mistake in the calculations. All right, so these are 3 examples where you can see that it's very handy to be able to use the distributive property or the commutative property of addition inside infinite sums. But you can only do it if you know that you have convergent series that you're working with. Okay, here we have find all values of x for which the series converges. Then state the limit as a simple expression involving x. Well, fortunately, this is a geometric series, so all we need to do is write it as such. This would be 1 over 2x to the k, from k equals 1 to infinity. Now notice, x is just a variable. K is the counter. K is what's changing. And we want to know for what values of x will that be in absolute value less than 1? Because whenever this has absolute value less than 1, this series will converge. So we just need to solve 1 over 2x, the absolute value, less than 1. Well, this means I'm going to take reciprocals. This means that the absolute value of 2x would be greater than 1. And that means then that either 2x is greater than 1 or 2x is less than minus 1, which gives us x greater than 1/2 or x less than minus a half. So these are the values of x that make it converge. And let's see, what would it converge to? Well, it's going to converge to the first term when k is 1. It's going to converge to this raised to the k power, so that's 1 over 2x over 1 minus r, 1 over 1 minus 2x. Multiplying by 2x on the top and the bottom, I get 1 over 2x minus 1. So this function, f of x equals 1 over 2x minus 1, is just a little rational function. It looks like 1 over x, but it's slid a little bit to the right and has a vertical asymptote at x equals 1/2. And that function is identically equal to this series, but only on the interval minus infinity minus a half and the interval 1/2 infinity. Between negative 1/2 and 1/2, this series does not add up to this. Just a little review, if any of you have forgotten how to solve absolute value inequalities, you're going to need it throughout the rest of the course. If you have the absolute value of something, let's just say star, any expression, if the absolute value of it is less than some number a, that means that whatever that expression is between a and the opposite of a. Whoops. And if you have an expression, the absolute value of star is greater than some number a, of course in both cases a has to be a positive number. If it's greater than a, that means that either star is less than minus a, or star, whatever that expression is greater than a. So the first thing you do is you write your inequality in this form or this form, like I did up here, and then take off the absolute value signs. And you take off the absolute value signs always either this way or this way, depending on if it's less than or greater than. Here we are to find the sum of the series, or say why it diverges. Now really all we've got to go with, all we've got right now in our toolbox is, well, you might have the test for divergence and find that the limit of a sub n is not 0, in which case you're done. It diverges. Or you might have the harmonic series. You know that the harmonic series diverges. We're going to prove it at the end of this lecture. You might have a geometric. Geometric series converges if the absolute value of r is less than 1. You could have a collapsing series where you would have to use partial fractions to write the term as something that will collapse when you plug in the values of k equals 1 to n. And then you could actually get an expression for Sn and take the limit. And that's about it. That's the toolbox that we have. So let's do these. We're going to use those tools. Well, is it equal to anything? Let's check first. Check first the test for divergence. We have a power of k over a power of natural log k. No, that's not going to have a limit of 0. We know that k over ln k squared does not go to 0. You would use L'Hopital's rule twice to show that this term a sub k does not have a limit of 0. Therefore, the series diverges. The series diverges by the test for divergence. So there's nothing to do. You just notice that a sub k doesn't go to 0. The next one, well, I don't see any pattern here, but that's no problem. We can just add those up at 6. So this is equal to 6, and then let's put it into 6 plus, and then put it into summation notation. These are powers of 1/3, so I'll write 1/3 to the k. From k equals, well, it's from 1 to infinity. Alright, so this does converge, and it will be 6 plus. The series converges to the first term, 1/3, over 1 minus r, 1 minus 1/3. That's equal to 1/2, so converges to 6.5. Another example, well, we always look at the nth term first, and we see the nth root of n goes to 1, so 1 over the nth root of n does not go to 0. So since a sub n does not have a limit of 0, Sn diverges. The sequence of partial sums will diverge, meaning that, of course, the series diverges by the test for divergence. Just put TD. Two more examples. Let's write this in summation notation. We have the sum, and let's see. The denominators are odd powers of 5. So that's going to be 5 to the 2k plus 1. That's how you write odd numbers, 2k plus 1. And the top is 3 all the time. And k, well, our first exponent is 1, so k starts at 0. So k equals 0 to infinity. All right, well, this clearly is going to be a geometric series, but we need to know for sure what r is so that we can calculate what it converges to if it indeed converges. So let's see, I would write this as the sum. I'd take the 3 and 1 factor of 5 out, which leaves me with 1 over 5 to the 2k. Oh, well, that is 5 squared, 25 to the k. So I will write it this way. The sum from k equals 0 to infinity, 3/5, which I could factor out because I see r is going to be less than 1. And I have 1 over 25 to the k. So it is a simple geometric series that will converge to the first term. When k is 0, I have just 3/5 over 1 minus 1 over 25. And that is equal to 5/8. So the series converges to 5/8. Here's another one that will be geometric, but we have to play with it a little bit. We have the sum from k equals 2 to infinity. And let's see, that's 2 cubed, or 8 times 2 to the k over 5 to the k. Oh, well, it's just 2/5 to the k. So it will converge. 2/5 is less than 1. It starts at 2. It converges to the first term, 8 times, well, that'll be 4 over 25. 2/5 squared over 1 minus 2/5. And that is 32 over 15, if I calculated it correctly. 32 over 15. Well, this lecture has been all problems and examples like you'll have in your homework. But let's add one little bit of theory before we finish. Let's prove that the sum from k equals 1 to infinity of 1 over k, the harmonic series, let's prove that the harmonic series diverges. And you just need to know that. Okay, well, let's see. Let me take red here, and what I've done is I've got the graph y equals 1 over x graphed here, and I've got these blue lines coming down from the integer values of x. So this is the point 1, 1 here. And what I'm going to do is just give ourselves some left rectangles. So this doesn't take long at all. It's really easy to see because we now know about improper integrals. So just imagine doing that all the way out, and look what this summation 1 over k is. Each width of every rectangle is 1, and the height is 1 over 1, the second one 1/2, the third one is height 1/3, the fourth one is, so this here is just the sum of the areas of the rectangles. It's just the sum of those areas. Well, the area under the curve from 1 to infinity is smaller than that. We're talking about all the areas of the rectangles. There's a little bit more than there is under the curve itself. So we know that this is greater than the area under the curve, which is the integral from 1 to infinity of 1 over x dx. We have already shown that this diverges. So if this sum is bigger than the integral, and the integral gets large without bound, we can say then for sure that the harmonic series diverges. So this is the last slide. How do you think we could use the fact that the harmonic series diverges? You've seen several examples where we have used the fact that we know when a geometric series converges or diverges. But this is also very helpful. This is called a P-series. We'll do more of it, I think, lecture after next. But let's see. What if we were given this series? Summation 1 over n, the square root of n, will converge if the limit as n approaches infinity, let me change this to a k, from k equals 1 to infinity. If the limit as n approaches infinity of the sum from k equals 1 to n of 1 over the square root of k is finite. That means it has a finite limit. What is this right here? Well, that's Sn. That's the nth partial sum. If the sequence of partial sums converges, the series converges. But look at that partial sum. The sum from k equals 1 to n of 1 over the square root of k is greater than the sum from k equals 1 to n of 1 over k, right? This denominator is smaller than this one, so this quotient is greater than this one at each value of k. So the nth partial sum of the series that we were asked about is greater than the nth partial sum of the harmonic series, and we know that the limit of the partial sums of the harmonic series diverge. So therefore, Sn diverges. And this is like a comparison test. You're not going to do any problems with this for your homework, but take a look at it because that's what we're getting to, is a comparison test for series.